So, last class we are discussing about the how to optimize a functional. Functional is nothing but a function of a function. So, if you recollect this one, that our problem is there that A is a point and B is another point. Then our problem is to minimize J is a functional which is expressed mathematically T 0 to T f, agree, then V x of t which is a function of x dot of t and t dt. So, this point A is a point, B is a point, both the points are fixed and this is the t and this is x of t, agree. So, A and B both are fixed, that time at time t is equal to 0, the point A and its coordinates is, you can say this one t 0 x of t 0, this one, and this coordinate is at time t is equal to t f, this coordinate is t f x of t f. Our problem is to find a trajectory between the two fixed point A and B in such a way, so that the functional is optimized, either maximized or minimized, that is our problem. So, let us call this is our optimal trajectory x star of t, and near about this optimal trajectory there is another trajectory is there which is neighboring of this trajectory, that is called, that is A star. So, x a is equal to x star of t plus delta x of t, this one. So, our problem is, I told you, find that the optimal trajectory x such that this functional is minimized. So, for that one, if you recollect, we consider first that what is the incremental, what is called functional, agree, that means del j we found out, and del j is a two parts after doing the Taylor series expansion. Then their first part of what is called is the necessary condition for the functional to be minimized or maximized, and second variation in functional, this is the first variation of functional we denoted by del j, and second variation of the functional is del square j, and higher terms of the Taylor series expansion we have neglected that if this. So, our first condition, this delta of j is the increment of the functional, agree, increment of or change in functional values, and delta j is first variation in functional value and delta square j is second variation in functional value. So, our first condition is delta j must be equal to 0, that is the necessary condition. In order to get this one, we got it in step 3, if you recollect yesterday, that what we got it that del j is equal to t 0 to t f delta v x dot whole transpose, and this value evaluate, this is the nothing but vector, this value evaluate along the trajectory, then multiplied by delta x. Delta s is the change in coordinates of x when it is moving along the neighboring trajectory of optimal trajectory x star. And then second part is del v del x dot t whole transpose, and put this value, evaluate the value x is equal to x star, x dot is equal to x star multiplied by delta x. So, this second term of this one, yesterday we have shown how to simplify this one. The second term I have written it here, see, instead of delta x t, by definition d of dt delta x t into dt as it is. So, nothing but it is, if you consider this is a v delta t you can consider is a something like this cancelled. So, delta v d del dv, and this whole quantity is known to use, which is constant. So, u dv integration from 0 to t 0 t f I can write is nothing but a u v and its limit 0 t 0 to t f minus v del v del u, this is the del u, and I multiply dt and dt this one. So, these things this term we can express into sum of two terms. Now, look at this one, because both the points are fixed, a point is fixed along the optimal trajectory or along the perturbed trajectory, which is very close to the optimal trajectory. Both the ends a and b are fixed. So, our this delta x t, if you see the, since both the ends are fixed, then I write delta x at t is equal to 0 is nothing but a 0, and delta x t is equal to t f is equal to 0. Since if you see our delta a of x t is nothing but a x star of t plus delta x of t, and t is equal to t 0, x of t 0 and x of x star of t both are at the same point. So, delta x t must be 0. So, that is why this is there. Similarly, at t is equal to t f, here at t is equal to delta x t, t is equal to t f, delta x t is 0, because x star of t and x a star of x a t is equal to t f both are same value. So, delta E is 0. If you put this condition here, the first term will not come into the picture, only this term. So, this the second term of this first variation of functional can be written as this term when both the ends are fixed. So, keeping that things in mind, delta j, now I can write it here. If you use the this expression in equation number 3, then I can write it. You see, this limit is t 0 to t f, delta b transpose this, when x is equal to find out this value, x t is equal to x star, x dot t is equal to x dot star into delta x. This is replaced by this one, d of dt del v x dot of t transpose, evaluate these values, x t is equal to x star t, x dot t is equal to x dot star into delta x. I have considered, let us call x is a scalar variable, x dot is a scalar variable. So, whether you multiply, because delta x I keep it here. So, if you do this one from equation 3, I can write from equation 3 and using the expression and replacing that del v dot del x dot of t whole transpose x t is equal to x star of t, x dot t is equal to x dot star of t delta x dot of t into dt, that things again whole thing. So, this limit is t 0 to t f. This I can replace by equal to minus, that means from equation replacing that quantity, means this quantity is replacing by this one, t 0 to t f d of dt del v dot del x dot of t whole transpose, put the values, evaluate the values, x of t is equal to x star of t and x dot t is equal to x star dot of t. Agree? This in this equation you just put it, then into this, into what we can write it, this into our del of x into dt. So, if you put in equation 3 replacing this by this, then finally we will get the expression like this way, integration T 0 to T f, T 0 to T f, and this is a del V dot del x t whole transpose minus d of dt del V dot del x dot of t whole transpose, that this curly bracket, then put x t is equal to x star of t, x dot of t is equal to x star dot x dot star of t into delta x t into dt. So, if you put this equation in place of this here, and after simplification I will get it this, let us call this equation is 4. Now, this is left hand side is a delta j. So, in order to become that functional to be optimized either extremal or minimal, then what is called this del j must be 0. If you recollect our lemma which we will discuss yesterday, that if T 0 to T f and g of t delta x t into dt is equal to 0, if and only if g t is, and g t is a continuous function, g t is equal to 0 for any value of any for every not for every point over the interval T 0 to T f. That means, this quantity is 0 if and only if necessary and sufficient condition g t will be 0 for every point over the interval, if it is so. So, I will apply this lemma here. So, you see whole thing I can call g t, which is a continuous function at t is equal to x t is equal to x star and x dot is x dot star, because I am doing the Taylor series expansion around the point x star, around the optimal trajectory path. So, this is our g t, this is x t, this is not equal to 0. So, this quantity will be 0 provided this is equal to 0. So, using the necessary condition for optimality, del j must be equal to 0, and by using lemma we can say this del j will be 0 provided this equal to 0. This implies using that lemma, that what we have discussed now. Our lemma is there, g is a continuous function over the interval T 0 to T f, and this g t if you have multiplied by non-zero delta incremental change in delta x into t over the interval T 0 to T f, it will be 0 if and only if g t is 0 for every point over the interval T 0 to T f, that is this. And using this lemma I can write that this 0 means this must be 0. So, our del V dot del x of t, agree, because this is a column vector transpose row vector multiplied by delta x. If it is x is a multivariable case, if it is a single variable, transpose is not necessary, agree. So, this transpose d of dt, agree, del V dot del x dot of t whole transpose, this you evaluate these values at now x is equal to x star, x dot is equal to x dot star. I simply write star means x t is replaced by x dot star, x t is replaced by x star of t, and x dot t is replaced by x dot star of t along the trajectory of optimal trajectory path. So, this equal to 0. If you write transpose, that will be 1 cross n if x is a vector. Agree? If you remove this transpose, then it will be 1 cross n. If you remove the transpose, then it will be a, if you remove suppose we remove the transpose, this will be x of x t minus d of d t del v dot del x dot of t. Agree? This evaluate this value at x is equal to x star, x dot is equal to x dot star. If you evaluate, this value is equal to 0, where the dimension is n cross n. So, this equation is known as, so this equation is known as Euler's Lagrange equation, and it is the necessary condition for the functional to be optimized, either maximum or minimum, but it is the necessary condition for this one, a function to be optimized. Next, we have to check whether the functional is a minimum or maximum, that sufficient condition we have to check it. It is same as what we did it for the what is called static optimization problems. So, and if you see this one, v is a function of x and x dot and t. So, if you differentiate this one with respect to x dot, it will be coming function of x, x dot and so on, and again you have differentiated with respect to t. So, this will be a second derivative of x will come. So, this is nothing but a second order differential equation, and second order differential equation if x is a single variable case. If x is a vector, then we will get for n 2 n differential equation from this, because for each variable x 1 we will get 2 differential equation. If we have a n such variables are there, the function, that integrand part, that v is expressed of this, the integrand part of this integral, this, and this x is a n cross 1, then how many variables are there? N variables. For each variable we will get second order differential equation. So, altogether it will be a twice n differential equation. In general, these differential equation are nonlinear time varying equation. So, if you solve this Euler's equation, you will get the necessary condition for this one. So, the solution of this one, and it is a, you can say it is a, if x is a scalar, then it is a second order differential equation. If x is a vector of dimension n, then it will be a twice n differential equation, they are coupled each other. So, now in this, next is the solution, the curve x star of t, a solution of Euler's equation x star of t is equal to x, which is a function of t, c 1 and c 2, and c 1 c 2 are the initial, what is called not initial, integration constant. Suppose x is a single variable case, it is a second order differential equation. We have a 2 integration constant, and that integration constant can be found out from initial and final condition of the problem. Suppose x is a n variable case, then we will get that how many constants are 2 n constants we will get it, and that 2 n constant we can find out by using initial and final value conditions. So, if you make it the remarks about the what is called Euler's Lagrangian equation, and this is nothing but a what is called necessary condition if functional is to be what is called optimized. This is the necessary condition. That means, what is the necessary condition? Del j is equal to 0 implies that Euler's equation must be satisfied, this Euler's equation. For that one, you find out the solution of x of t, and that is the optimal trajectory which will give you the minimum or maximum value of the functional. So, this now remarks on what we have seen. Euler's equation is a nonlinear differential equation. Why it is nonlinear? Because after getting the Euler's equation, you will get this is the product of either x into x dot or x dot into x double dot or x square into x dot or x square into x double dot and so on. So, it is a nonlinear differential equation. First remark says the Euler's equation may become nonlinear differential equation. Since products or power of x double dot t, x dot of t and x of t may appear in the Euler's Lagrange equation. This is first thing. Second thing, that what is called knowing the initial and final value, the 2 point initial and final point, because x may be n dimensional, but one point is there a, that is what we have considered. Knowing the initial point a and this is the final point b, there are 2 points are there. In that sense, it is called 2 point boundary value nonlinear differential equation. 2 point boundary value problem. The T W T 2 point T P B V P 2 point. Again, the solution of such type problems, nonlinear differential equation, is not a easy task to do this one. So, generally people can solve this problem using the what is called numerical technique. One can use numerical technique to find out this one. Next point. So, your things solution of nonlinear T P B B P is quite difficult analytically, quite difficult in analytically, difficult task in analytically, agree, but and often solved with numerical techniques. Yes. Third is, if Euler's Lagrangian equation is satisfied, that it indicates that Euler's Lagrange equation is satisfied, it indicates that we have a extremal value of the function, either minimum or maximum. If does not satisfy the Euler's equation, agree, it indicates that functional value j does not have any optimal value of this functional value, if does not satisfy EL conditions. So, we can write the first remarks, the EL equation, Euler's Lagrange equation is not satisfied for any function this indicates that the optimum does not exist for that functional. So, we have to satisfy this one, otherwise this does not exist for the optimal value of the functional. So, let us see in multi-dimensional case now, that I told you if it is x is n variables are there. So, we will get 2 n differential equation, okay, 2 n coupled differential equation which we need to solve for finding out the solution of what is called optimal trajectory x, which will optimize the functional. So, now more multi-dimensional functional, just extension of single variable case. Suppose j is a function which is a function of x 1 t, x 2 t dot dot x n of t, and it is also function of derivatives x dot of t, x 2 dot of t dot dot x n dot of t, and this is function of time, which is equal to is t 0 to t f v x 1 of t, x 2 of t dot dot x n of t. Similarly, x is derivative, it also depends derivative dot dot x n of t dot into t and dt. So, this is the multi-division. So, what is the necessary condition for, let us call, two fixed point? Both the points are in n dimensional space, that we have a 2 points are there A and B, and both the points are fixed. That means, optimal trajectory starts with a point and ends with B point. That means, it starts A point and ends with B point, and neighborhood, this is the optimal trajectory for the functional to be optimized, and neighborhood of this optimal trajectory there is another trajectory x a t, which is equal to x star of t plus delta x t, which is very small perturbation from along the trajectory x star. So, both the point are fixed, but we have a n dimensional variables this one. So, what is the necessary condition? Necessary condition when both the points this is a point are fixed, is same as this one. What previously we used to write a t, if you see that one, our this differentiation of a scalar quantity with respect to a, if it is a scalar with respect to x, then this differentiation of this with respect to x is a scalar. Suppose x is a vector, then differentiation of scalar quantity with respect to vector, which will give you the column vector, is nothing but a gradient of v with respect to x. This is nothing but a gradient of v with respect to x dot, and then because if you do this one column vector and then you multiply it by differentiate with respect to time. So, in short, if I write it like this way, it is nothing but a gradient of x, gradient of which function v dot, which v is function of x dot of t and t. You take the gradient of s with respect to x, this indicates with respect to x, agree, with respect to x, minus d of dt, take the gradient of x, gradient of v x of t, x star of t, x dot of t, t. So, you get the take the gradient of v with respect to x dot, agree, that you that you multiply the differentiate with respect to this, then you will get it right left hand side. So, this is the Euler's equation, but I am writing same equation only using the symbol gradient here. So, that equation will be n cross 1, that one. That means, each, if you see this one, del v of del x 1, del v of del x 1, del v of del x 2, del x 1, that expression del v of del x 1 minus d of dt del v del x 1 dot is equal to 0, agree, is equal to 0, whose dimension is scalar, that right hand side. That means, it is a second order differential equation, because I am differentiating with respect to x 1 dot with respect to time, it is a second order differential equation. So, and if you see this gradient of b with respect to where, you can write where gradient of b with respect to v is function of x, x dot of t, and I am doing with respect to x is nothing but a, it is nothing but a del v dot del x 1, del v dot del x 2 dot del v dot del x n. So, what is the dimension of this one? N cross 1, and each is a x 1, x 2, x 3 is in dimension is. Then gradient of v with respect to x dot, what I will write it? Same thing, del v del x 1 dot del v del x 2 dot and dot last will be del v dot del x n dot of t, this, and this again dimension is that, and this quantity again if you differentiate, you see what you will get it. This is the function of x 1 dot, you will get it, then again you will differentiate x 2 double dot. So, whole expression, Euler's expression for each variable, you will get second order differential equation. We have a n such differential equation, we will get twice n differential equation of that one. So, and ultimately if you write it this one, I can write it del v, this expression mod x I of t minus d of dt is equal to del v with respect to x I dot of t, this whole thing is equal to 1 cross 1, and I varies from 1 to n, because we have a n variables are there. So, let us call, now we go instead of a specific problem, both the ends of that our trajectory is fixed, then we can go for more general problem. So, our problem, more general problem is like this way, one end is fixed, other end is free. So, one of the end point is fixed, while other is free. So, let us see the corresponding diagram for this one. Our job is here, this is the functional, which is a function of x t, x dot of t and t, t 0 to t f, b x of t, x dot of t, t dt. Agree? We have to find out the trajectory of x t, optimal trajectory of x, such that this functional is optimized, either maximized or minimized, and what we making, one end of this trajectory is fixed, other end of the trajectory is free. So, this is the one and this is the other point is b, agree. Then you have a this is the T f, this is the fixed point A, which is time t is equal to 0, this time is free T f plus delta T f, and this is our optimal trajectory. We assume this is the optimal trajectory, which will minimize this what is functional. And near about the optimal trajectory, there is another trajectory is there, x a of t is equal to x star of t plus delta x t. Okay. This point is D. Okay. So, now and we have a this point, if you see this one, what is this corresponding coordinate of this one B? B coordinate, what is the coordinate of A? Immediately I can write it, coordinate of A x t x t 0 of t. What is the coordinate of B? Is nothing but a T f x of T f, x star of T f. Agree? Or you can try x star of this one, x is T f, these two coordinates. Now, so our point C, this is the point C, and coordinate of point C is what? C, T 0 plus T f. And what is this one? That value x T f, t is equal to T f, x T f plus x T f plus delta x T f. So, or you can write it x a T f plus delta T f. What is this coordinate? So, this nothing but a x star T f x star T f plus delta x T f. X star T f is what? T f plus delta T f, and x is equal to t, t is equal to what? T f plus delta T f. Agree? So, you see t is what? T is x T f plus delta T f, then this is T f plus delta T f, that is what I am writing, x star T f plus delta T f value and delta x T f plus delta T f. This is the coordinate of this one, and let us call this value is what is called B point is free, is not fixed, it can be anywhere, here, here, here. Now, from here to here, what is these values? At t is equal to T f, what is the value of that one? Is nothing but a delta x at t is equal to T f, delta x T f. Then at this point, at time t is equal to T f, what is this one? This is nothing but a delta x T f plus delta T f, agree, which I am denoting by a delta x f, delta x f, agree, this one, and this is delta x T f, and this value if you see this one is nothing but a delta x t is equal to T f plus delta T f, which I am writing in x, delta x suffix f. So, this is 0, this is time t, and this is the value of x of t expression. So, our job is here, one point is fixed, this is the fixed point, and B point is free. So, what you have to find out? You find out B point is free means x star T f is free, T f is free. So, our job is to find out a optimal trajectory x star t such that this functional is, this is T f, that functional value will be optimized. Then this is our problem, but B is free. So, Now, near about the optimal trajectory, we have considered another neighborhood trajectory of x star is x a t, which is x star of t delta x t. So, now we can describe these things like this way. Let the left hand point A is fixed, right hand point B is free. Our problem is, just now I mentioned it, our problem is to find a trajectory x star of t starting at point A, on which our problem is find a trajectory starting at on which the functional value j is equal to T0 to Tf b x t x dot of t dt can achieve its extremum value or extremal value, can achieve its extremum or extremal value. So, that is our problem. This is our problem. So, we will proceed in the same manner as we did for the 2 points of the trajectory is fixed. I will just identically we will proceed in the same manner. So, our solution, if you see, that is why we are considering that we have a adjoining, we are just joining A and C. Consider an adjoining trajectory specified by x of t is equal to x star of t plus delta x of t, joining which 2 point, A point and C, joining t 0 x of t 0 agree or x star of t 0 and T f plus delta T f and x star of t, you can write it x star, no problem, plus delta x f. What is delta x f? Delta x t is equal to T f plus delta t, which I am writing delta x suffix f, that is this one. So, now what we will do it first, again you first find out the incremental value of the functional, that means del j incremental value of the function, but now our time is, you see, from t 0 to T f plus delta f time interval, because t is free. So, it is t 0 to T f plus delta T f, that is, if you see that one, this is the delta T f, and our functional value is along the what is called adjacent trajectories, that means x v of t x star of t plus delta x of t in comma x dot star of t plus delta x dot of t, again this into time, this is the function of time already we have written of dt, minus t 0 to T f v t x star of t plus x dot star of t dt. So, this is the incremental value of the functional, and it has a two parts, because if you consider the Taylor series expansion in the same manner, that will keep the first variation of the functional and second variation of the functional. Other variation of functional is neglected, because delta x is very close to the optimal trajectory of this one. So, its cube we are neglecting. So, so for a necessary condition, what is the necessary condition? The first variation of the functional value will be 0, assigned to 0. This is our necessary condition. So, let us call this is equation number 1. From equation number 1, what we can write it? I split up into T 0 to T f plus T f to T f plus delta T f, this integrand part. So, from equation 1, delta j is equal to T 0 to T f V t x star of t plus delta x of t x dot star of t plus delta x dot of t, this into dt plus T 0 T f to T f plus delta T f. Okay. So, this part I split up into two integral part, this and this is argument is same, x star of t plus delta x t plus x dot star of t plus delta x dot of t dt minus whatever the along the trajectory T f along the optimal trajectory this V t x star of t x dot star of t dt. If you recollect this one, from this and this one, we have computed this one earlier case when both the points are fixed, this we have done. Only the difference when both the points are we have already done, only the difference is that here that one end point is fixed, another end point is free in this problem. So, let us see, let us call this is the equation number 2. Okay. So, now we consider mainly concentrate with this term, the second term of equation 2. Consider the second term of 2. So, what is the second term of this 2? T 0 T f to T f plus delta T f V t x star of t plus delta x t plus x dot star of t plus delta x dot of t, the whole dt. Now, look there at this point, you find out this integrand part of this one value along the neighborhood of the optimal trajectory, the function value. This is a scalar quantity. Find this scalar quantity function value along the what is called neighborhood of that optimal trajectory, what we have considered x a of t, along that one you find out the function value for each time up to t plus delta T f. So, what we expected? It is something like this. So, let us call it is something like this. It is T f, I am just magnifying that one, is a T f plus delta T f. What is this? Area under this curve during this period, that means this one. If it is a V t x star delta x t, then we along the x a, and this is x dot star t plus x dot dot of t, if it is this one. What is this area under this curve? I can find out, because delta T f is very small, though I am amplified to show you this one. This nothing but a area approximately I can write it area under this rectangular curve. So, this I can write it. What is this point at T f? What is the value of function value of this one at t is equal to T f, this value function, agree, that means this multiplied by this. So, this rectangular area will be same as the whole shaded graph, because T f is very small, even though so amplified this one. So, I can write it this is nearly equal to, if you see, nearly equal to V t x star of t delta x t plus x dot star of t delta x dot of t. Find out the value of the function at t is equal to T f, that is what I am telling. At t is equal to T f, you find out this value, and this ordinate multiplied by epsilon delta small delta T f is your what is called area under this curve into delta T f. This is the area under the approximately, because T f is very small. So, this I can write it this nearly equal to, if you do the Taylor series expansion of that one, this it is nothing but a V t x star of t plus x dot star of t, agree, this plus V dot of this x of t whole transpose, agree. If it is a vector, then this transpose is vector. If it is a scalar, transpose is not necessary at all. So, this if you are, because this Taylor series expansion at t is equal to T f, t is equal to T f, because first I will write the Taylor series expansion, then I will whole thing I will write t is equal to T f, this into delta x del of x t plus del v dot del x dot of t whole transpose, then your because along the trajectory of this, then this is equal to x dot of t, agree. This whole thing nearly equal to, I have written it that one, agree. And what is this value? I am around the x star, that is why x star I have written in this one. That whole thing, if you write from here to here, evaluate at time t is equal to T f multiplied by delta T f, agree, multiplied by this. So, if I push it delta T f here, delta x t into delta T f, both are very small quantity, you can neglect that one. And if you do this one, delta x dot t is also very small, delta T f is small, this you can neglect. So, this whole quantity after multiplying by delta x is delta t, you can neglect it. The whole quantity after multiplying delta x dot to t, you can neglect. So, naturally this equal to del v x star of t x dot star of t, t is equal to T f into delta T f, that what we just mentioned from the graph. This you see, value of the function at t is equal to T f V f function multiplied by delta t will give you the approximate value of the area under this curve from when you are integrating T f to T f plus delta T f, but delta T f is very close to T f this. So, this is the important relationship, we got it this one. So, if you see this one, this whole term, this the second term of this one, I can just replace by this one. Now, what about these two things? We have seen earlier these two terms, we can further simplify, because you do the Taylor series expansion of that one, then this and this will be cancelled, agree. Then first term of this one will left over here, agree. So, if you see this one further, that let us call this is equation number 3. We have given equation number 2 here, this one, the whole thing, then equation number 3 is that one. Using equation number 3, using 3 in 2, we get first variation of the functional. del j is equal to T 0 to T f. I am not repeating this one. What I did it here, if you recollect this one, this term you do it as before when both the points are fixed to do the Taylor series expansion, then first order terms, second order terms you retain it and higher order terms you neglect it. Then you will get it this type of things. Del v dot del x of t whole transpose star del of x t minus d v dt, that del v dot del x dot of t whole transpose star del x dot of t, this, then this whole thing is dt, plus there is a initial and final condition is there, del v dot del x dot of t whole thing transpose del x t when limit is from t 0 to t f. Please see our earlier derivation plus that term. The second term of this one we have shown it is nothing but this term, then that term is v t x star of t plus x dot star of t, this t is equal to t f into delta t f into delta t f. Now, see this one, the a point is fixed, delta x term will not be there at t is equal to 0, but only the t f is free. So, this term with delta t f will be there as it is, it will be there and this term will be there. In out of this lower limit and upper limit, lower limit will not be there because a point is fixed, delta t x is fixed, delta t x is 0, then only the upper limit of t f will be there. So, we will see next class how we will simplify ultimately what is the necessary condition we will get to find the optimum value of the functional. So, we will stop it here now.